Stanford University.
Hi, welcome to EE380 Stanford Computer Systems Colloquium. It's fall 2011-2012 and we're getting into the middle of the quarter. This is the time when people tend to drop a lecture or two behind. As I'll point out towards the end of the quarter, if you're 1 or 2 behind at the end of the quarter, you've got a good chance of finishing. If you're 3 or 4 behind at the end of the quarter, not so good. Just for those of you who are taking the class for credit. Today's talk is about one of the worst modeling problems. Not only is the data bad, challenging. Not only is the data bad, but the interactions are extremely complex. The time periods are long, so you don't really know if you're right. But the numbers are so large that all of the rent seekers are out in full force. Today's speaker, John Weyant, Professor of Management Science and Engineering, has been working on such models for the IPCC and the state of California, among others.
Happy to be here. This is a challenging area, so for people who work on complexity and uncertainty, we need your help big time. I'll give a few background comments on my background. I started in aeronautical engineering, which is helpful once you get back into climate, but then I went into operations research, economics, public policy, and so on. And I actually run an institution called the Energy Modeling Forum that's been around for roughly 34 years. And then about halfway through my run on that, and I've been around about 32 years, about halfway through my run, I got pulled into the climate game, mostly because the early models on the policy side, in other words, what to do about climate change, were energy models to which people added first just carbon emission coefficients and then other gases. And then as time went on, these got integrated with representations of the climate system, atmospheric chemistry, and the various impact sectors. So as my introduction was perfect, it described how complex this system is, because you've got to really know well and integrate physics, chemistry, biology, economics, sociology, psychology, politics, and so on, which makes it a pretty daunting task. So. No, I did once get cross-examined by the head of the International Federation of Churches. So these things come in. There's actually a good point on a serious note. There's a very big kind of north-south, rich-poor dimension to the politics surrounding climate change, which comes through the IPCC and other venues. So for this class, for this session, I'll try to not dwell too much on the politics, which could take long time, but I'll mention kind of in passing a little bit about that. I would like to start with a little bit of background on climate science for those of you who aren't intimately familiar with it. It actually turns out that the Earth is enveloped in a blanket of so-called greenhouse gases in the atmosphere, which includes carbon dioxide, methane, CH4, and nitrous oxide, N2O. There's a natural level of those gases. For carbon dioxide, it's about 280 parts per million, which is what you would have seen, say, the century before the start of the Industrial Revolution. And that, of course, has gone up, which is part of the problem. Another thing that creates a great deal of complexity is one of the more efficient greenhouse gases is water vapor, also natural. So there's both a need to account for that in general and a really complicated set of calculations one has to do if one believes that increases in human-made greenhouse gases actually stimulates the formation of water vapor, i.e. clouds. And not only that, you not only have to know where the clouds are, but what kind of clouds they are. Are they kind of so dark that no light gets through them in the first place, or are they kind of letting the shortwave radiation come in from the sun and then kind of trapping like the other greenhouse gases and so on. So I'll come back to that in a second. It turns out you can pretty easily calculate that the so-called global mean surface temperature, which is the statistic the climate modelers like to use, which is for any given year, the average temperature of the surface atmosphere averaged across the whole globe. With no greenhouse gases naturally occurring, the average global mean surface temperature for the planet Earth would be about minus 15 degrees centigrade. So if we just think about that a little bit, it would be a lot colder all over the place. With the natural background levels, i.e. non-anthropogenic levels, it's about plus 15 prior to any additional greenhouse gases and climate change. So far, since the beginning of the Industrial Revolution, it's known with some degree of accuracy that we've increased the temperature, global mean surface temperature, by about 0.8 degrees centigrade. It's been calculated by other climate scientists that we're committed, meaning the stock in the atmosphere, because of the time lags in that affecting the climate, we're committed to about 1.3 degrees C, and most projections of anything from a pretty steep reduction in greenhouse gases almost immediately to kind of a status quo base case takes you maybe another 2 to 4 degrees C by the end of this century. So a high projection might be 5 or 6 degrees C relative to pre-industrial, and a low might be somewhat over the 2 degrees C that the policymakers seem to have rallied behind as an aspirational goal. And if you work on this stuff from the ground level, you wonder what they are thinking when they make these commitments. This would, it is actually still possible, but it would require almost immediate global cooperation and near to a cessation of any additional emissions. So it's a great aspirational goal unless you start banking on that being the outcome. The National Academy study I was involved in a couple of years ago, I was on the advancing the science side, and we met with the 4 panels that kind of adaptation and impacts, the mitigation, the science, and the communicating to policymakers. And the big problem with this aspirational goal is the impacts and adaptation group actually thought that 2 degrees was a high. That was the worst it was going to get. So they pulled together all the scientific evidence up to 2 degrees C, and they said, oh my God, we got to go back and look at it. So it gets pretty, you can get pretty far out of whack between the political aspirations and the reality on the ground. So so pre-industrial CO2 concentration was about 275, 280 parts per million by volume in the atmosphere. The climate scientists started by looking at scenarios, interestingly, now policy relevant. They're just made up a doubling of CO2 concentration, so they would run just the climate, just the atmosphere models with that kind of step function or ramp to those levels. Ironically, it turns out that's probably something we could do without too much trouble if we cooperated and had good technologies, and that would lead to about a 3 or 3.5 degrees C increase in global mean temperature over the course of the century. A key statistic for the operation of the climate models is the climate sensitivity. So that is the change in global mean surface temperature for a doubling of greenhouse gas concentrations, which I just kind of set up. And that, the mean from the IPCC right now is about 3 degrees C, maybe a little bit less, not too much. This has bounced around not too far from 2.5 or 3 degrees C for 20 years. The models are better, we understand more, but that's kind of where it is. The range, sort of 1 to 1.5 standard deviations, I call it, although it's not been precisely demonstrated, is kind of 1.5 degrees C to 4.5 degrees C. That seems like a big range. So that's the range amongst the so-called global circulation models, the climate models, which in the last IPCC round were, in fact, coupled ocean atmosphere models. So they basically have many layers. They have grid cells that are on the order of 100 kilometers down to about 10 kilometers on the side. They basically just use conservation of momentum in 3 dimensions, conservation of mass, and conservation of energy, and a little bit of accounting for fresh and salt water and stuff like that that tends to matter. Ocean currents are largely, not largely, but significantly affected by the salinity in the water. So we have the conveyor belt that takes the hot surface water from the Gulf Coast up to Europe, northern Europe, and then it gets the right density that it sinks down and then gets returned underneath the surface on the bottom of the ocean. Current global emissions, so now I've gone from temperature back to concentrations. Emissions of CO2 for one prominent greenhouse gas, about 20 billion tons per year, so it's a lot. It's in carbon terms, it's about 6.5 or something like that. So there's a lot. So each year we kind of increment the stock in the atmosphere by 1 or 2%, but this keeps going kind of up and up and up. So it is a long-term problem. One significant thing from a policy point of view is in terms of the carbon dioxide, there's a little bit of a wrinkle in this for the so-called short-lived gases, the aerosols, is that carbon emissions anywhere affect climate everywhere. So the global mean surface temperature goes up, that leads to a pattern and a change in the general circulation. And whenever you emit a ton of CO2 anywhere, it has impacts everywhere. Right now, another interesting thing is out of that 20 gigatons of CO2 that are emitted, about half stays in the atmosphere, only half. About a quarter, we think, gets absorbed in the oceans. About another quarter gets absorbed in the so-called terrestrial ecosystems. In other words, it gets warmer, more CO2, plants like CO2, they grow more if they have the other nutrients around. So already you're seeing some ecosystem complexities and so on. A big worry is, as you might imagine, this works great for a while, these kind of storage bins for carbon. But as the loading continues, we're not really sure whether there might be what's generically termed a tipping point. So we would go from the ocean, remember all your, I think it's Le Chatelier's principle, the chemical, absorption in the ocean, and the same thing for the biosphere. If everything burns out, then it's all going to get released at one fell swoop. So there is a fear that at some point, if you push this system too hard, it's nonlinear enough and onerous enough that you would get a big reversal. So rather than the ocean and the terrestrial biosphere being a sink for carbon, they would turn into kind of sources. So that's a fear. That's probably a little bit away from our current operating point, but over 100 years, who knows? In addition to that, there are two pernicious complications in figuring out what this climate sensitivity is going to be, looking at historical data, say. And those are the long time it takes the ocean to come to equilibrium. So the deep ocean is very deep and very cold at the bottom. Having studied a little bit of heat transfer, I always found it difficult to get my arms around a system where you did a delta change in forcing, and it took 200 years to come to equilibrium. So what you're doing is you're kind of progressively warming the deeper reaches of the ocean, not for a while, but for 200 years. A lot of the climate scientists want us guys, the people who project emissions and mitigation policies, to go out 200 years, so we're sure we really see that kind of commitment on the ocean side, which would affect the equilibrium temperature, but also the thermal expansion of the ocean and sea level rise. The other thing is this aerosol cooling. So we emit partially and unburned, mostly hydrocarbon molecules into the air. This has to do with diesel engine combustion and other coal combustion, and on the one hand, and biomass burning, both the commercial type we'd like to see more of, maybe, if we knew how to do it right, but also a lot of traditional fuels. A lot of parts of the world, they just burn a lot of biomass. So this creates aerosols. Some of those are actually greenhouse gases, but on balance, they're the opposite of greenhouse gases. They kind of provide a shading. So two things about this climate response is we don't really know whether we've had almost complete or large response over the last 20 years to the forcing that's occurred. So with little lag, or it's just the start of a very long time cycle, the fact that we have the aerosols offsetting further complicates the problem. But through statistical analysis of straight historical data and model runs, we have some feel for this 1.5 to 4.5 degrees C. Yes, sir.
What about methane? You hear things about, you know, the Canadian and Siberia giving off all this methane, which is tremendous greenhouse gas.
So that's another nonlinearity. The background level is pretty low. You could get a big burp, a big release of those things. So there's lots of these kind of potential tipping points. That would be another tipping point. There's clathrate, you know, very high pressure, low temperature deposits of natural gas in the bottom of the ocean. Some people want to use those as an energy source. They're also a potential place. The methane molecules are not as long-lived as CO2, but they're actually more potent greenhouse gases. So you get kind of funny pyrotechnics. But I don't want to make this whole thing on climate policy. So this is just one segment of the climate policy problem, and that is just understanding the atmosphere-ocean system. And I've kind of snuck in a little bit of what I would consider, what you could think of as the kind of terrestrial ecosystem, which is sometimes referred to as that green slime model. Is that, you know, if you've got certain conditions, stuff will grow more. If you don't have those, if you have the dry, hot conditions, they won't grow as much. No people yet, no human activity, nothing else. So one thing we do with the integrated assessment models is we try to bring those in. The climate models are in parallel, trying to add humans now to their system. But up until the last, actually up in the first couple of IPCC rounds, they just did the climate system. The last couple of times they've been able to do coupled ocean atmosphere. This round, the fifth round, they're actually doing these kind of green slime, you know, terrestrial ecosystem things. Nothing that appears in this report will have a formally linked kind of endogenous human component. We are working on this at a research level, both from the socioeconomic side, adding in the science pieces, and the science people are now just starting to experiment with taking some of our socioeconomic modules and sticking them in the big climate models. But for this class, this lecture, the amount of complexity and uncertainty is almost overwhelming at times. The intergovernmental, national, I forget what they call it, the 15 big national science, national academy, sorry, inter academy thing did a pretty major review, which I testified 3 times before, and their number one suggestion is to do a better job of communicating uncertainty, which I certainly agree with. And actually, some of the uncertainties were just brought up in the Q&A here. I certainly agree with that. How we're going to do that, we kind of need your help on how to do that.
More refinements, whatever. Doesn't that also generally increase the variance of your prediction, or is it going down?
We don't know. I spent last weekend with the leaders of what you could think of as the decision theory, decision analysis community, and they were very concerned about this, that we were, and I pled partly guilty, that we were trying to resolve things by adding more complexity, and it isn't clear that actually works. There is kind of a disjuncture between the kind of policy decision-making focused perspective and the science for science sake perspective. So I was on Pam Matson's panel in the National Academy study, and we wanted to say integrative science is the way to go. You got to understand all these linkages and use that to sort out what's really important and set priorities for science. Unfortunately, half of the 20 people on the committee were running big science programs, and they said, whoa, wait a minute, does that mean that you guys that do integrative stuff is going to get more budget? You know, and then you have to go back and say, you're the guys that can help us figure out how to do the integrative stuff and set priorities. But it's, I'll tell you, you probably have all seen this, it's a hard institutional barrier to jump over. So we basically said, we think all areas need an increase in funding, but if you're going to do an increase in funding, it should be proportionally weighted towards this integrative stuff, because it's only a small fraction of 1% at present.
Well, that's a comment that Keeling made when he was alive, and I had a chance to hear him talk about
Excellent.
Stuff.
Cool.
The uncertainty quantification, the SciAM, the Applied Math Professional Society, is holding a meeting on the topic next year. on uncertainty quantification. My question, though, is, I was on the periphery of the atmospheric community. They put their source code for all their set of models on the web. Is your source code openly distributed amongst the people, the community, and how do you guys do changes to that, or are you guys keeping it playing the source code?
That's a great question, and actually jumps ahead a little bit on the talk I was going to give, but I think it's important enough I'll answer it now. So historically, most of the integrated assessment stuff and the socioeconomic stuff has been kind of research grade models, not what we consider to be production grade. As I'll show just very briefly, we've kind of focused on insights and kind of flexible versus more flexible policies are better and things like that. Now that we've joined into the forecast accuracy space that the climate scientists, they would really like to get a better idea of the shape of this distribution for climate sensitivity and many other dimensions of it. We've actually gone pretty swiftly in this direction. The political climate, so we were affected as much, except for a few people, by ClimateGate than the climate modeling community, because now people are saying, well, your tools are used for public policies internationally, nationally, and state of California, say. You need to, A, make your tools more transparent, and B, do some kind of model validation. We'll come back to the model validation, but the answer to the question is, if you asked me that question 3 years ago, I would say no. I was trying to do classes 5 years ago, and the students couldn't get a hold of any of the models to run. Now we do. We have about 8 of the big models up and running, and it's just been, and that's us, Stanford people with, computer science stats people around. I think it's just getting to the point where there are kind of publicly available models. So one of the big teams in the US, the so-called Joint Global Change Research Institute, Pacific Northwest Labs, University of Maryland, was asked just 2 years ago to have a public version and to have a kind of user group type support. So they have an annual users group. It now has 70 users in it. So we're working to catch up to where the climate community is. I actually have a joint project on model validation with the group at Livermore known as the Program on Climate Model Diagnostics and Intercomparison, PCMDI. They have had something like 20 times our level of funding for 20 years. So they have done a lot with making these codes and results from model runs publicly available. And we brought Carl Taylor, the director, over to Vienna 2 weeks ago to talk to the European members with a bunch of the European groups along about how to do this and so on. And my conclusion there was we're behind still, but because we've been able to leverage off where they have gone, and it's the technology that makes this easier to do anyway, we're rapidly catching up to them, but we're still not there. And this will, I predict, be an issue with even the current IPCC round, although we're working kind of full throttle on we have through EASA actually a kind of global database of all the results of all the scenarios used for all the writing, and we're now trying to link that into the climate network because they have both the Livermore hub, they have 3 kind of base stations that have all the data and a bunch of satellites that you can link into. So we're trying to get ourselves to be a socioeconomic side, kind of a node on that network.
Given the limited funding that integrated assessment has had so far, does opening this thing up open more points of attack for climate change deniers to come after it, okay? Or is it, on the balance, closing more holes and making the argument stronger?
So far so good, but I wouldn't want to make a long-term prediction about whether it's good or bad. For me personally, I just felt we had no choice, that we were going to get accused of all kinds of things. That leads to my first slide here, which is a cartoon. Actually, I gave a talk to these decision people last week. And I asked if there are any climate skeptics, and we spent an hour responding to all the climate skeptics. So just in case you were wondering if this occasionally gets political, this is kind of an interesting picture. I could actually give cartoons on the other side of the aisle also, but this one just struck me as being kind of funny. So if it's okay, I'll just kind of plow ahead up. So I'm going to talk a little bit about what is integrated assessment. You already have a little bit of a flavor for that. The types of models that have been used, what the contributions have been in the past and could be in the future. This I already gave in response to your questions. We kind of did these insights, you know, what's a really bad thing to do, what's a really good thing to do. As we get closer to potential decision making, we got to come up with kind of more refined estimates and so on. And that's something the climate and the ecosystems people want us to do, because they've been really working on this forecast accuracy issue. And I'll show you just a few examples of that. I'll talk about approaches to uncertainty analysis, approaches to setting policies in light of all this complexity and uncertainty, and a little bit of reflection on the difference between the way the natural sciences and the social sciences approach some of these kinds of problems, including building models, designing scenarios, developing approaches to uncertainty, and approaches to model validation, which is something I spend a lot of time on. So there was a couple of years ago a DOE Office of Science Biological and Environmental Research Integrated Assessment Research Program workshop, which I was one of 20 people in. Tony Janatos from the Joint Global Change Research Institute, who's a kind of NASA alum, world-class ecosystem guy, kind of wrote up the final report. We all wrote pieces, but he kind of stitched together. So what is integrated assessment? It's focused on the connection between human systems research and energy. In this case, this is Department of Energy. So if you went to NOAA, they would say it's weather. If you went to the Dutch integrated assessment team, they would say it's ecosystem modeling, because that was the base of their model. As we leveraged off energy models, they leveraged off integrated ecosystem modeling. Integrated assessment models integrate natural and human climate science, and they provide important science-based decision support tools. I would say for me, this field started about 20 years ago, maybe a little bit more, and the big hope was you would get things from integrated assessment not seen through models within the individual disciplines. And I have to say honestly, and you'll see some examples here, we didn't really get there until about 3 or 4 years ago, where you can actually see some of the major interactions and feedback. So I'll kind of stress those in some of the subsequent examples. So IAMs draw from and serve over the climate science communities. That's great. It's exciting. It's fun to learn. Warren Washington at NCAR, who won the National Medal of Science last year, has an excellent book called 3D Climate Modeling, in which he goes through all the physics. And then when they ran out of data and we're at the wrong scale, he would say, we parameterized and it's really solid. We parameterized, it's not too bad, and we made it up. Which only somebody with that stature could actually get away with. If I tried to do that, I'd probably get slaughtered. So that's a challenge. The other thing that I've already alluded to, before you get to the outside politics, is the internal sociology and politics of the different disciplines. They're interesting, but you know, you kind of look for the people that you can work with. In fact, this new scenario design we're running outside the IPCC, but inputting back into it, wasn't even our idea. This is on emission scenarios. It was Jerry Meal, who's the big, one of the big guys at the National Center for Atmospheric Research. So mostly I know a guy who gets some research support from DOE. So this is a US GCRP picture from way back when. This is what I was talking about, is we had kind of an end-to-end version, and we said, well, integrated assessment is really looking at all the interactions. So you start with kind of human activities, a kind of engineering economic models of the energy system. Maybe you have enough data to do agricultural, livestock, and forestry. You may or may not have enough land use data to actually run those sensibly, and we're now re-examining that. You would probably bring in hydrology these days, the coastal system, other human development. So this module kind of has models that produce emissions on the one hand, experiences economic impacts around the horn here, secondarily, and also is where you look for mitigation options. So, and possibly some adaptation, ideas for adaptation. Although most of those have come from the physical, so far, the physical models over on this side. And that goes up into these kind of atmospheric chemistry and ocean carbon cycle computations. So these are intermediate between the human activity and the climate system. So you have to kind of spread things over time and mix things together. It's a little bit complicated, you know, for things like ozone. Sunlight is also in the chemical conversion equations and so on. And then that leads to probably the biggest models here that up until recently kind of run in Cray days, so you can simulate one day in one day on a Cray. In fact, so they actually still sample, you know, various representative days and so on. It's a little bit better now as the computers have gotten much faster, but then they would like to use the compute power to have more resolution on the grounds that that's going to give them better predictability. But as was pointed out, they really need to test that, and that's probably true. Yeah, exactly. So, and that's actually now becoming true in all the impact areas. The biggest models are these computational terrestrial vegetation ones. Some of them are pure green slime. Some of them actually have vegetation competition and choice. Some are linked back to economic systems where you look at the land, you compete it from, you know, between recreation, agriculture, and now energy crops is the big new thing. And I'll show a couple results for that. And then that kind of physical impacts feeds back into human activities. So back in the day, I used to give this talk and say, suppose you were smart enough and had the data and you knew every piece of information at the right scale to go all the way around this horn. You could downscale climate results. You had the perfect physical system models. You even had the kind of macro economic impact things. So you could queue up all the quantitative and qualitative impacts of climate change that you could think and that the policymakers want. How close would you be to being finished with the problem? Because different actors, different stakeholders have different perspectives on values, you still wouldn't be that close. So you've got a whole nother kind of game theoretic public choice set of issues to deal with. But it's a start. I mean, it would be good if you could actually know this better. And I think we do. I think it is true. There's been ups and downs, but I think we do understand the system a lot better now than we did 20, 30 years ago. So in the beginning of integrated assessment, there was kind of an interesting split. There were policy-oriented simulations, which basically were very science-based with lots of detail. These were mostly done in Europe, almost exclusively in Europe. So you would say, like a climate model, we have kind of cause and effect, and those play all the way out at the level of disaggregation that seems most useful. So you'd have ecosystem function and, you know, plants growing and trees growing or not growing and sea level rise and, you know, a little bit, not too much, of ocean acidification. Because as the ocean assimilates carbon, it's alkaline to begin with, but it becomes more acid, which makes it hard for shellfish and so on to exist. In the US, you could blame probably my strongest of many disciplinary ties as to economics. There was really a big push towards doing aggregate, and I'll show you one early and continuing example from my lifelong friend and colleague Bill Nordhaus, just to do kind of a cost-benefit analysis. So you would see the cost and benefits of doing nothing, and then usually the cost and benefits of control, which would lead to marginal cost equals marginal benefits. So this was both a kind of disciplinary split between, say, the environmental science crowd and the economic crowd. I don't want to put any value judgments on this at all. Just it was what it was. It is what it is. And it just so happened that I did the chapter in the second IPCC report, the first, last, and only integrated assessment chapter. And I'll try to explain why that's so. And we basically saw, kind of in stark contrast in our team, because we had Europeans and Americans in it, that the Americans all like this, the Europeans all like that. So what does it mean? Well, it may mean that when you do the cost benefit, you aggregate so much, you miss a lot, and people get hurt, and there's bad outcomes and bad income distribution, and you never know it. I'll give one example of that when we get into the impacts piece. On the other hand, what the cost benefit people will say, well, you know, we're going before Congress. They have a lot of things they can do and spend money on and, you know, attention on. So they need to know how big this problem is relative to other ones. They get different policy proposals, so they need a way to, you know, kind of calculate what a good policy might cost to reduce emissions, say, versus a bad one. And my personal favorite is, if you're into decision theory, if you're able to put numbers economic numbers on these, you could do a value of information calculation and therefore compute using whatever you want, Bayesian updating, compute the value of additional research in each of the key science input areas. And that, I think, maybe you don't want to take those numbers too literally, but they are suggestive, I think. And then you look for, on top of that, these tipping points or thick tails in probability distributions.
Also, because of research, the outcome of research and the value of research.
You try. I asked, see,
it's always positive, right?
Yeah, I always ask the decision people this, is that question is how do you know which way it's going to go? And the other thing is the unknown, unknowable type things, because there is still a fear that there are impacts out there. I started with a summer workshop almost 20 years ago where we brought the impacts community together with the climate modeling community and our guys. And I thought it would take 2 or 3 years, and we didn't even have a good list for the first 10 years, and now we're still not sure that we have the complete list. I always tell a story. I was a peer reviewer for some reason of the acid rain program back in the 80s, and they were doing sulfur. Everything was focused on sulfur. So we kept saying, are you sure sulfur's all you need? So they spent, half of the $500 million budget over 5 years. And so year 6, we had a review meeting. And they came in and they said, oh gosh, we looked at this again and we really need to do nitrogen and particles as well. And we said, eek, you have everything queued up and all your authors recruited and models built to deal with only sulfur. And now you're telling us the science wasn't completely that much settled, but they were sure in the front end of this. So back to why do you do integrated assessment modeling? I did a postdoc on models and policy at Eastern University public policy program, split half in Washington. And I used to ask people, what do you think the biggest impact of all this analysis is on policy? Or actually, the uniform response to this day, when people really think about it, these are people who have actually done things that have affected policy, is the biggest impact is to avoid truly disastrous policies, nothing optimal or Pareto improving or anything demonstrably Pareto improving. What is it doing?
Hit OK.
Yeah. So what the models do in a complex system like this is they at least provide some illusion, if not reality, of internal consistency. We have worked on insights like the 4 flexibilities, and this is we've actually done in congressional testimony is, okay, Mr. Policymakers, you have lots of things you're trying to do with all the giveaways and bounding the problem and different interest groups, but to the extent you can do it, it's best to allow emission reductions to take place where they're least expensive, when they're least expensive, because you've got this kind of common pool, accumulation issue, through whatever policies seem the best. I'm a big advocate of advanced technology research like the GSEP program here to kind of make the technologies better in 20 years, so then the policymakers won't say it's too goddamn expensive to do anything. They'll say, oh, well, if that's what you need, we have these, really good solar cells or carbon capture and sequestration at a reasonable cost. Let's go ahead and do it. Then finally, what we called wet flexibility was just bringing in the other greenhouse gases. We did a whole study where we went after Kyoto. There was the 6 Kyoto gases. There was only data and modeling on one of them, carbon dioxide. So we got in with a bunch of data development people, and then at least we have those 6. We're still trying to get in all the aerosols and so on, because those turn out to be important. So you can get rough numbers out of these, maybe at some point to guide policy development. You can use them to prioritize research. And you could do, if you're interested in this forecast accuracy thing, and I'll show one or 2 examples of that, you can put probabilities on future climate outcomes. So you could add to the uncertainties on the climate side, which people had already been thinking about, this rate of thermal ocean uptake and the aerosols effects, a few factors like that, or just the climate sensitivity per se. You could add uncertainties about socioeconomic drivers within the context of a particular policy regime. So uncertainty, there's kind of sensitivity analysis, qualitative measures, decision analysis, stochastic control, robust planning, computational statistics, qualitative. People have kind of thought about using all of these. I kind of like a combination of qualitative and quantitative measures. I think there's no dominant winner at this point. I'm trying to push, from my perspective, not do it, but push people who could do it to pursue a lot of these more in reaction to this inter-academy review thing. So here's kind of IPCC standard. This is actually from the third assessment report. So this is one reason the negotiators haven't liked integrated assessment is because you get things that look like they might be answers, like what they should do. And this sometimes makes them nervous, sometimes not. So I can, if you want, kind of floor of the assembly, 500 policymakers and 10 analysts getting beat up stories, I can give you those. But so they actually think of the three working groups, the kind of emissions and mitigation, the impacts and adaptation, and the science pieces as being kind of their little integrated assessment playground. So they would actually like to link them together. And there's some argument that the analysts blow it when it gets too hard linked. So I can believe that. I'm not sure that's what always happens. So this is actually a range of projections of CO2 from the so-called SRES, the previous round of scenarios, developed within the framework of the IPCC. We argued strongly after that the IPCC should not develop its own scenarios with its own chosen people and then pretend that they're evaluating those relative to all the other scenarios in the literature. This seemed like some kind of conflict of interest. So unfortunately for us, Chairman Pachauri said, okay, you're on, prove you can do this. And we said, where's the funding? And they said, well, you didn't mention anything about that. So we're I think, doing a pretty good job. So this is a wide range of projections you can see in terms of CO2 concentrations, because it's kind of this bathtub, 1 or 2% a year deal. The range of concentration projections for that range of emissions is somewhat smaller. The SO2 emissions in the previous round were very high, and then people said, what about health effects in these developing countries? There's only so much coal you can burn before people start having pretty bad health effects. So the previous round before, this is 20 years ago now, was here, and the SRES scenarios were there. There's now a little bit of debate about whether in countries like India and China they're going to be quite that sensitive to the health impacts, but there are definitely limits to how far you can push it, and people have put kind of numbers of deaths and economics things on it. So then you take this stuff, and usually this takes kind of a round to the IPCC, so you're out of sync. So we designed a parallel process this time. But then you run it through the big climate models, and you get two things. You get temperature change, range showed here, 1.5 to 4.5, a little bit more for some kind of extreme members of the ensemble of climate models, and then sea level rise, where you get, in this instantiation, maybe 3 or 4 tenths of a meter. These were upgraded by about 50% or a little bit more in the fourth assessment report amid controversy that with melting glaciers and so on, it should be higher. So some climate scientists claim that in this round it'll be as much as 2 meters expected, with, again, a lot of uncertainties and tipping points. That's an interesting story. Originally, it was known that there was kind of second-order physics revolved around ice sheet melt. And they were kind of ignored, as used to do fluid mechanics, higher order terms, to be ignored kind of thing. So you can think of it like a little pool of water would show up on a hot day, and then like a cavity, it would, in your teeth, it would kind of be frozen over the next night or something like that. But the people actually went out and measured and then went back to their textbooks and saw that the thermal transmissivity across the boundary was such that, and the observations supported this, that the water got hot and then it just kept burrowing down and actually got to what was called, it was kind of unfortunate, depending on which side you're on, term the kind of bedrock, meaning you could kind of skid big hunks of ice off. And we still don't know a lot about that whole dynamics, but I think people were pretty surprised about that, although Richard Alley, yeah, so you get lots of complications when you've got an ice shelf in there. Richard Alley just got the first Steve Snyder Communicating Climate Change Award or will get awarded. It's been announced at the AGU meetings here in December for being the ice sheet guy who now has like 3 PBS specials on this exact topic. So I won't talk more about it. But you know, I know him pretty well. So I said, okay, Richard, you told me sea level rise was kind of a millennium scale problem, and now you say you don't agree with Al Gore that it's kind of 50 years, but it could be 200. I may be slow, but what's to say I don't come back to talk to you in 5 years and you say, oops, we blew it, Al Gore was right all the time, and we're going to go underwater pretty quick here. So that's another kind of uncertainty tipping point annoyance. So this is kind of I call this example number 1 of integrated assessment. This is kind of the IPCC thing. As I mentioned, I don't want to get too much into the problems with this. What would happen is we do the scenarios, the integrated assessment community, which would do our socioeconomic part. We would do these things. The carbon cycle guys would take it. The atmospheric chemist would take it. They'd feed it into the climate models. And if you were lucky in a kind of 6 or 7 year IPCC round, you would get consistent climate outputs. But the other work group 2, which is on impacts and adaptation, would not have those available. So they'd be one whole cycle behind, and then the next round they would pick up the old stuff. And of course the science improves, the models improve, so it was a disastrous thing. So I'll give one plug for our actual approach this time, suggested by Jerry Meal, a climate scientist, was to start at the middle and have essentially a radius forcing or concentration starting point, and then have both groups work towards that so the impacts community can start much sooner. In fact, they have the climate simulations already in this round with over 2 years to go.
The most amazing divergence there is the predictions in CO2 emissions. Between the optimists and the pessimists, there's a huge chasm.
Yeah, so this, another long story. So this was designed to be kind of 2 by 2 scenario design where you had either a cooperative world in which economic growth was very rapid or very slow, and where a concern about environmental issues was either very high or very low. So if you had a lot of concern about the environment and with these two here, and either high or low growth, that was okay. If you had kind of runaway cooperative growth but no concern about the environment, you got kind of China on steroids, I guess, is the high one there. So that's something, getting back to probabilities, that we'd like to kind of disentangle for both the baseline and the control scenarios, and that's actually one of the examples I have. So with the climate modelers knew that there was this issue with uncertainty about their wares, about so these are indexed by the actual emission scenario. So this is one of the low scenarios, this is a middle one, this is a high one, and this shows the distribution in 2020 to 2029 and 2090 to 2099 here. So it shows both the mean and the kind of variance. But this is just for the in this case it was ocean atmosphere kind of projections. There's a little bit of sidebar on whether this really is a complete probability distribution. I think it really just focuses on what they believe are the biggest sensitivities. So all the surprises are not included in that.
My favorite question. The mean is going up and everyone talking about it. What about the variance? Looks like the variance is worse. The variance will catch up with us.
That would be
the mean really gets dangerous.
Yeah, that would be my personal model.
I mean, the hurricanes or whatever,
yeah, if I was
the unpredictable events are coming in fast. But then
yeah, and this I think there has been, because of the complexity of the problem, a focus on the means and not the extremes. Yeah. This is what you're saying. And yeah, I think, you know, we made some huge mistakes when we started doing sea level rise. It was kind of like the big problem is this kind of steady state ocean pre and after climate change averaged over, you know, decades. And in point of fact, the big problem is that the sea surge is much more significant for the surge conditions where you have a big storm coming through, and that's where all the damage, you know, 90% of the damage occurs from sea level rise. Is not you kind of, you know, go underwater and have to have a snorkel or something like that. It's these really extreme storms that have much less resistance and can wreak havoc on your people and structures and so on. So what IPCC did, unfortunately, a couple things happened. On the impact side, There weren't really comprehensive models, standardization of measurement, not much economic valuation, so it tends to be quite descriptive. So that characterized the first 2 rounds. In the 3rd round, the impacts people said, well, we're concerned about a lot of stuff, and we need a way to communicate it absent having the funding or the smartness or the data to do more increased things. So what they started doing is counting up actual studies from their disciplines that were not definitely the results of climate change, but consistent with what you would expect to see in climate change, both in terms of the global mean temperature and their particular region. Well, one problem is most of the impacts take place in a specific location, so the translation from global mean surface temperature to the temperature, precipitation, soil, things like that is a much more complicated calculation. So they came up with a couple hundred in the 3rd assessment report. Last report it was up to 1,000 things. So you can't say it's definitely climate change, it's a coral reef problem, but it could actually be lumber practices where you get a lot of essentially sawdust clouding up the water so the sun doesn't get through the coral reef. And a lot of them you can't really disentangle that. But it's unfortunately very qualitative. So I was actually in the 3rd assessment report team that tried to do this kind of qualitative thing. In the 4th assessment report, they were a little bit more precise. So they have the impact sectors here, at least what they consider to be the big ones. And then they have some kind of rough signposts. So for ecosystems, you have up to 30% species extinction. For this, unfortunately, they did relative to current climate, not historical climate, 1980 and 1999. And then you start losing more and more species as you get higher. So my reading of this and the way I think we did it in the National Academy report was, you know, up to 2 degrees C, you have some bad, some good, some really bad. You know, it's kind of a mixed bag. Nothing really ominous. By the time you get to 4 or 5, everything looks bad. It's hard to find things that look good. One of the decision people challenged me to think of somebody, you know, they wanted to go to Canada or Russia and have the tundra be appropriate for growing crops or beachfront property or something like that. So maybe there's a few people that are still doing okay out at this level. I will tell one story on this distributional equity thing, and that has to do with food. So all the early global climate perturbed ag studies said, don't worry, for 2 degrees C increase relative to pre-industrial, stuff's going to grow more, you're going to be better off. In fact, you're going to gain, sorry for the economist speak, $100 billion discounted present value from 2 degrees C. Good, not bad. So this went on for about 5 years, and people actually looked at the details of the calculations, and they actually showed that the $100 billion discounted present value was composed of a $1.1 trillion gain in the industrialized countries of the, quote, north, because they weren't near the thermal limits of the crops or could switch to different crops, and a $1 trillion discounted present value lost in the countries of the south, the poor countries. So this, of course, when it hits the floor of the negotiating sessions, is kind of political dynamite, only exceeded, hate to give anecdotes, but they're kind of meaningful, only exceeded by the numbers for the value of statistical life. So people went around and they said, okay, how much does each country spend on occupational health and safety regulations? Both, you know, formulating and enforcing them, but modifying industrial behavior. And it actually turned, not surprisingly, it turned out that a statistical life in Europe or the US is worth about 20 times one in India and China. So this, unfortunately, wasn't reported as the result of an interesting calculation, but an actual measure of the relative value of a life in the US and India and China. And that one I remember because it was in Montreal or someplace. I was sitting in front of the Chinese and the Indian. The alphabet worked out with the rows, and they were about hit the ceiling. So underneath some of the aggregates, even when you do this kind of regional disaggregation, you have that kind of thing. So my friend Bill Nordhaus back in 1980 said, geez, it would be nice to know how big the problem is and how it relates to other things and so on. So he basically set about first a static and then a dynamic attempt to say, okay, well, you have emissions here. If you're going to use policies to reduce them, it's probably going to cost money. Otherwise, you would have fewer emissions to begin with. And then more difficultly, as the carbon emissions or carbon equivalent emissions go up, the damages of climate change will get more. You've already drawn out of me that this is very uncertain and could have a lot of jumps and twists in it. But he said, okay, let's do a quadratic that seems to fit the evidence that we have, although meager. He called a bunch of us, this is a true story, over the weekend and said, okay, the US economy, about 0.5% of economic activity is in extremely climate sensitive sectors, but that's, the US doesn't include non-market. For non-market, we'll double it. For developing countries where more activity is outside, we'll double that and we'll get 2% for a 3 degrees C. And that became a number that he thought would go away in a couple of months, and to some extent it still exists today. And people are doing more detailed analysis, but kind of using that as a benchmark number. So in his most recent book of 4, Question of Balance, which is a play on the Al Gore book with a similar name in 2008, he actually put out kind of a temperature change and implied greenhouse gas or carbon tax trajectories. So a couple of interesting things. As I mentioned, the policymakers' favorite is this 2 degrees C here. Another scientist / policymaker favorite policy is 2 times CO2 or 550 CO2, which is a little bit higher, a little bit lower in terms of CO2e. And then I won't go through the slams of the Stern proposal. It's a lot of personal back and forth between all of us on that. But and then he computed his optimal, which was his based on pulling together the evidence on the mitigation side, mostly from our studies, and what little cost information there was on the impact side from that community. He got this kind of optimal trajectory here, which kind of goes up to 3.4. Now that's much lower than the baseline, which by his simplified climate model was about, by 2200 anyway, was about 5.5 degrees C. His current number, by the way, interestingly, for various reasons I won't have a chance to get into, is just about 3 degrees C. So to me, an interesting thing was he was slammed by the people favoring the 2 degrees C and the 2 times CO2, but they're actually not that far apart. And both of them, or all of them, are far better than kind of the business as usual. We'll see this story emerge again in a couple of minutes. These are the carbon tax. He wanted to show that the Stern and Gore proposals would cost a lot. His optimal is here, the 2 times CO2 is here, the 2 degrees CO2 is here. It's actually not that far away. If you added uncertainty, and he's actually done this, you get even closer to 2 degrees C. So it's not that far off. He actually, in his book, people didn't necessarily read this, has a whole chapter on could you do 2.5, and he's not altogether a dismissal of that if you had the political will to go ahead and do it. So as I mentioned, a lot of our work led through kind of big model comparison studies, roughly 15 models, integrated assessment models for each. We went through this. It's very advantageous to control emissions where it's cheapest to do so, when it's cheapest to do so, within the kind of averaging accumulation period. How you do it, I won't have a chance to go through all these because I want to get onto some truly integrated things. These, by the way, we've done mostly, I told you before that we cheated, mostly on the socioeconomic side. So you could think of these as having a lot of climate content, but most of the argument we made before the technical work groups for the negotiations and the US Congress were mostly this kind of socioeconomic thing. So it's you've decided to control emissions. Here's some advice on how you ought to think about doing that. You ought to design policies that are flexible in these 4 ways. Here's just one example, recent one from this DOE report where you've got a 4.7 watts per meter squared target, which is probably a 3.5 to 4 degrees 3, and a 3.4, which is down maybe 2.6, 2.5 degrees. And we have, we've done a whole bunch of variants on this, but first best and third best. So if developing countries delay coming in, that's kind of third best. If they come in immediately, you convince them or incentivize them to do it. That would be the first best thing. They have this kind of odd optimistic, pessimistic. Optimistic in this case means you don't recover very fast from the worldwide recession, so you have a low baseline. Pessimistic means you're swimming in dough and money. but you have more emissions. I could never talk them out of that nomenclature. It's just one of the, it's a model actually developed jointly by Stanford and EPRI. As I mentioned, a big issue that really begged people to do more integrative modeling is biofuels, the wide-scale biofuels. Why? It's because when they first put in biofuel estimates into the integrated assessment models, they got really good results, and then they looked at what happened, and you can probably guess what happened. They forgot about the rainforest, so they cut down all the rainforests and planted biofuel crops. And then people said, well, that means our carbon cycle isn't kind of hooked up or working well, because that means you immediately lose more on the carbon, because basically they burn down the rainforest in order to clear the land, so all the carbon goes up like that. I said, well, that doesn't sound so good. And they said, well, how can we do this? Well, let's put a constraint or a price out that carbon alongside the industrial emissions and grow crops on marginal lands. And he goes, well, what's marginal land? And does it really not compete with crops? And do you have water and fertilizer and things like that? So I went through a whole other round with the marginal land not being so marginal. So it got more tricky to do. This particular result is kind of a canonical key one. This appeared in Science magazine a couple of years ago. So this basically shows the base mix of land cover. This shows if you do this kind of uniform carbon tax, you don't get this huge increase in bioenergy crops and huge reduction in unmanaged. So this is unpricing those. So what you have to do, because you've cut down the rainforest, is you've got to take the industrial emissions and really, really go down to compensate. Crazy, I know, but it's not like policymakers wouldn't think that they were being optimal around the world and truly responsive to the threat and actually do something like this. So it was kind of a seminal article in that regard. But it took a lot of work, because in order to do these kinds of trade-offs, you have to have good land use information. You have to know where the crops are growing. You have to know where the water is. We're getting better at that. I would say in this round it wasn't good, so this is going to change. They're now one of the groups that are using their model within the context of a community climate model. And they're now finding that the changes in land use emissions, when you have a fully coupled system, because you have the climate feedback, are much bigger than they thought, by at least an order of magnitude. So stay tuned for that. That's kind of, yeah.
So did those models, I remember reading that, but it's been a while. Did they actually predict something like the almost tripling the price of corn because of the corn ethanol subsidy?
They did, yeah. They did just that, yeah.
Right.
And they predicted the malnutrition that occurred?
Well, not directly, but you could see these things happen. And you remember what happened when people said biofuels is the answer. Right. You had the Mexicans saying, well, we can't buy tortillas because all the U.S. guys are using up all the corn for the biofuels. And I think I was in China. The premier of China said biofuels is the way to go. He says, I got this big, population that's almost starving anyway. You think I'm going to push them over the edge by doing biofuels to help you guys out with your problem in the first place?
Did they actually come to the conclusion that the net efficiency is 0.3%?
More like 0.15.
Okay.
Yeah, that's kind of this is the net reduction in emissions all on board with, farm equipment and processing losses. Now, of course, we have not to mention UC Berkeley, the Biofuels Institute there. We have a lot of research going on here on better crops and better conversion technologies, but the corn ethanol is a pretty bad loser. I mean, the only argument can make is it gets you started. I mean, there's always a silver lining. So some people will say it gets you started and the research will work harder. You'll get some infrastructure set up. But I personally think that's not, Congress kind of pushed that too hard, I think is what you're pointing out. So this is the MIT model, which is built around a lot more science. It's kind of the heavy science integrated assessment model. They have a 2D simplification of the GIST climate model. They have the community land model. They have Jerry Melillo's terrestrial ecosystem model, and one of the leaders is Ron Print, who's really a maybe the top atmospheric chemistry guy. Although they just hired Susan Solomon away from NOAA, who's probably the other top dog, so they're going to have monopoly in that regard. So what they did with the MIT model, because of all this chemistry, is they looked at a high pollution, high urban pollution, no greenhouse gas control scenario versus a greenhouse gas control scenario and criteria pollutants capped. And with the chemistry, they could actually look at the interactions between climate and non-climate policy. I don't have time to get into detail, but they could actually calculate the reduction in crop outputs and natural ecosystem growth using that kind of system, which seems pretty important if you're going to do a truly integrated analyses over a long time period. Another thing that MIT did with their model is said, okay, it's not just the science activities, I mentioned this before, it's also the socioeconomic uncertainty. So we're going to consider different control scenarios. We're going to do probability draws over the major economic drivers and the major climate drivers. And you get distribution like this for the base case is this high guy here, and the most tightly controlled scenarios there. Back on this point, not only does the mean go down, but the tail gets much less scary looking. The one thing they did do that was probably not smart is they said these are unbiased probability distributions. And I said, yeah, if the MIT model is perfect in translating all the inputs into all the outputs, a perfect model of the climate system, the ecosystem model, the economy, then they're unbiased. So we're actually trying to redo, Bill Nordhaus and I are trying to get all the models to redo this kind of thing. My favorite one, though, this is partly motivated by the late Steve Snyder. This is kind of the communicating to the public thing, and maybe to us as well. So this is a no policy emissions climate response probability wheel. So the area of the wedge shows the probability. So you get to spin, given all the uncertainties, you get to spin the wheel. So this goes up to 7 degrees, which I already says 6, 7, even 5 are all pretty bad. So you got more than half of that. Surprisingly, again, even at a 675 parts per million CO2e, which is probably a 4.5, 5 degrees C, even that seemingly modest level of control, the odds look a lot better. You don't go over 4, and you got kind of a 2/3 probability of staying under. This is Bill Nordhaus's 2.5, I think, by another name. So that's kind of how they're trying to communicate with the public. The guy that did this is actually working on some computational approximate dynamic programming approaches to get more dynamics in. This I criticized in the IPCC. Somehow this got in the IPCC report. It's got a little bit too advanced in the climate chapter, but not in the economics and policy chapter. It basically shows if you pick a particular level, according to these PDFs, what the odds are that you'll be able to stay, the probability that you'll overshoot the 2 degrees warming. The reason I say this is good, it kind of lays out some basic turf, but it's bad in the sense that it assumes that you pick a target and you stick with it for 100 years, 200 years. So I use the argument that your feet could be on fire and you could say, well, we bet on this outcome and it didn't work out, but we're going to stick to that target. So there's a time dynamics thing. So this is a tough problem, though, to get the compute power to do sequential decision making under uncertainty with Bayesian updating. So one of the decision theory guys said we should just use stochastic differential equations and we'd be fine, but that's beyond the state of the art, but actually a nice thing to shoot for. My colleague, now deceased, but a critical guy, the developer of the Stanford Integrated Assessment Model, Alan Mann, did a kind of 8-way model comparison. This is dynamics, but very simplified. So it says, based on surveys of experts, there's kind of a 90% of the probability distribution centers at 2 degrees C for the climate sensitivity, 2 degrees of GDP for a 2-degree temperature increase. If you take the upper 10% of the distribution, you get 4.8 degrees, about double, and a lot more economic one. This was a Morgan Keith, a very famous 16 climate scientist survey. This was Bill Nordhaus's 16, 8 environmental economists and 8 kind of ecosystem people. So lots of interesting why different groups got different results, which I won't have time to go into. And then you do kind of the normal sequential decision making under uncertainty, where either you find out now, you kind of act and then learn whether you're on the expected track or the extreme track, or you have to decide for a while before you know. So you have to kind of pick one particular energy system or one particular set of policies, then you find out just, and this is a little bit dated, like by 10 years. This is kind of a hedging diagram. So this is if you do no controls. The blue is if you knew you were in the kind of run-of-the-mill middle of the distribution case. The green, quite different, was already harbinged here. It's kind of the, you know you're in the extreme case right from the get-go. There's no uncertainty about it. That's what you do. This line here says what you would do if you were balancing the cost and benefits being wrong in either direction. You do this, and then once you found out in 2020, which is optimistic, people have done different dates of resolution, partial reconciliation, you kind of go down more towards where you would have been anyway. Now, a problem with this analysis on the policy side I pointed out is if you look at the prices, in order to pull this off, this 1 decade reduction, it's actually two decades reduction there, you would have to crank up the carbon tax kind of unrealistically from political views. And of course, there would be uncertainty and controversy and stakeholders and stuff. So for me, that just means I would put a constraint on how fast you could ratchet up the carbon tax. I won't say too much. I've gone through most of the examples. So what are you going to do is one issue you could address. And for me, we had a huge debate between Ken Arrow from here and Bill Nordhaus, who I mentioned at American Economics, about whether you want to always go for the ultimate cost benefit or you want to take your best shot, do a cost effective analysis at some target, and then reconsider 10 years later. That might be one way to go, as long as you do reconsider later and don't forget about it. I got in trouble because I was on the opposite side of my old boss, John Holdren, and John Schellenhuber and Bob Watson, three eminent scientists / climate scientists, and I said, well, rather than have the World Bank go for the 450 CO2e 2 degrees C as a recommendation, why don't we do a hedging strategy and go for 550 or 650, and then if things get worse, go. And they looked at me and they said, John, it's actually, it was a great argument you made 20 years ago, but what you were supposed to do in your interim is more research on climate impacts and climate system, more development of advanced energy technology, and what did you do? And then I said, well, we're writing on behalf of the developing countries for them. There's no way I'm not going to go with you guys and just say, you know, this is what we think you owe us, or we owe them in this case.
I'm a little concerned that you brought up the issue, and we all know this, that highly nonlinear effects, highly unpredicted effects, threshold effects, and so forth. Yet this economics, this 2% of GDP problem with 2 degrees rise and so forth, doesn't seem to take account of ocean acidification, which is looking like it could be the most immediate problem, and 70% of the human protein on Earth that we eat comes from the sea.
So in my set, I didn't do that part of the setup, but there's kind of 3 things that are kind of different to worry about, and I only did 2. You're absolutely right about it. I did sea level rise, and which is a little bit different than all the chemistry and stuff. All you need is the simple physics to do that, although they screwed up the simple physics. Ocean acidification, you know, the estimate is if you did one of these 550 or so scenarios, you would reduce the pH of the ocean by 0.2 on the pH scale, and that would lead to ocean species extinction, maybe 20% or something like that.
North Atlantic.
Yeah, so I think when we went through this, and I did that part with the decision, because we had 3 days with the decision theory guys, and we did decide the frame is too small for the actual policy thing. So we got, and I'm as guilty as anybody, we get into what we have models for and information on, and we forget about these. So these are not unknown unknowns or even necessarily tipping points. They're just other things that could be some of the biggest stakes for policymakers, mankind, humankind, that we need to get in there more explicitly. And that's why I like the decision analysis approach, because you wouldn't really need a big model to do that. You could use a big model, but you could just talk to the experts, which sounds like you've already talked to the experts.
Well, 0.1 pH away from
Yeah.
disaster as far as
Yeah.
plankton is
So
concerned.
why isn't more research being done?
Right,
in that
exactly.
area? And I think it's a lot of it's political. You know, again, people don't want us to do this value of information calculation, and I imagine if we were able to do that, and we're trying to get money from Gates Foundation or something. I guess it's one of the guys there was from Microsoft Research. To actually do that, a lot of the government people I think won't do this because it'll I don't want to be too pejorative, but it could affect the status quo in terms of research priorities and so on. But
Yeah.
the stakes are too high to allow that to continue. So these are just a few ways that people have thought about approaching this problem where you don't have perfect information. This is actually a wonderful example of kind of doing a broader kind of cost-benefit analysis. Yeah. Yeah. So I wonder. I need to check on this. I assume the IPCC science part is going to do ocean acidification. I hope. What's happening with integrated assessment and uncertainty is everybody's saying it's everybody else's job. So I actually have started an offensive on that. But this is another one, the ocean acidification, that I could just see work with one saying, well, it's not really the physics science piece of that. And the impacts people saying, oh, we thought the science guys were going to do this. So we here on the impacts one, Chris Field from Division of Global Ecology, Carnegie Institution, is the chairman. And the whole technical support unit is there. So they are quite open to people like us saying this. And what their strategy has been, because of ClimateGate and GlacierGate, probably read those in the newspapers, is if they don't have expertise in the group to get contributing authors who are, and or to insist that some of the external reviewers actually have expertise in those areas. You know, with the Himalayan glaciers, they got this statement by a guy who wasn't a scientist who just thought it would be provocative to say that, you know, within 30 years the Himalayan glaciers will disappear. And they went back and they said, who is this guy? And it turned out he wasn't a scientist. It was alleged that in parts of the review this actually came out, but they were too distant from the actual chapter, so they didn't change it. And they, you know, obviously that was Chris Field, eminent scientist, gunned up to do a great job this time. He spent half his time for 6 or 8 months at the beginning of his term answering questions about what went wrong. So hopefully through that in the National Academy, the Inter-Academy Review, we've kind of learned some of those things. But remember, when you do IPCC, it's almost all volunteer labor. So you have to make sure people are committed to do a good job. I'm actually a review editor this round, so it's part of my job to make sure. Fortunately, I can actually tell you things that I would be embarrassed by. But so far, there's been no scandals in Work Group 3, which seems surprising because that's where the economic stakes are. Now, that may be a political call that things are moving so slowly you don't have to worry about it. But that's why I think on the question before, we have to be much more transparent and much more careful as we get closer to actually costing people real money. Because I think then you're going to get these muckraking groups will come through and say, we can't find your model, we can't verify this, we can't verify that, and so on, which is what they've been doing with the climate modelers the last year or so.
Local problem. The problem is they don't know how to estimate the total future cost. In other words, what's our grandkids going to have to spend to hire the Dutch to come and build a dike under the Golden Bridge.
That's a subject for another lecture, an interesting one. Yeah. So we did.
The love of boats.
Yeah, Ken Arrow and I actually have been involved in the discounting debate. Ken's much better than I am, but I did a book that he helped me put together. But we had all the Nobel Prize winners had to either current or likely future, and a couple of them actually have gotten it in 1999. And we said, if we get real smart people together, they'll give us the number for long-term discounting. And the answer was, we don't know out of that. But we learned a lot about that. Part of it is that the people whose preferences you're trying to represent haven't been born. So it's a kind of deep set of calculations you have to go through. Yeah, if you're interested in that subject, Ken's kind of one of the, I would say, almost all these Nobel Prize winners, future Nobel Prize winners, were either protégés, colleagues, or students of his. So he's thought about this a lot, and also about social choice theory, which is really, that was my one thing with the decision theory people is, how can you use a single decision maker model when you have so, who makes the decisions in the USA now? what about the next administration? What about what the Europeans are actually going to do, the Chinese, and so on and so on? And my big puzzle for China right now is we've been doing these comparisons of the Chinese components of the global models with the local models. The local models are all rigged into the 5-year plans, which don't necessarily give you economic outputs, but China's China. So the question I have is a 5-year plan, what does it actually mean out 5 years? So, and you get answers from, it's the law, it must be so, or there's hell to pay. Or on the other extreme, we're the city guys, we have the state guys in between us. They're just it's just a bunch of hot air. We don't, we'll do whatever we think we need to do to maximize economic output because that's how we get rewarded. And everything in between. So I think that's another thorny problem. But I do like this, because I did this thing last week and a couple of you got right back onto it. If we're really going to think about an overall architecture for decision making, we've got to make sure our decision frame, if I could use that term, is as good as we can get it. And so the problem is people have gotten into their models, into the research programs, and they've kind of lost track of the need to always make sure there isn't something that you could have been paying attention to that you didn't, that comes back to bite you.
Stanford is very good at that. We have a lot of different Woods Institute projects and so forth.
Yeah.
They're all
Absolutely.
doing these things, and they all are not looking at the big picture.
Yeah, and I think it would be not that hard to take some of these same people and redirect them. So actually what happened was the guy that runs the International Institute for Applied Systems Analysis the last 3 years is a USC guy, a guy named Detlev van Wernerveld, who was a card-carrying member. So he's in my community up to his elbows the last 3 years, but he's a card-carrying member of the decision theory, decision analysis community. And so now we're trying to get at least those two communities, hopefully through places like Woods and so on, together to kind of compare notes on this. Because it's easy, if I go in to my guys, they say, well, what you say is right, but we don't have people who can do that, and we're doing the next grant or the next contract. But so you really need people to do the question of what are we doing here in the first place. I actually have Steve Snyder asked me to do it, an editorial on climatic change. And I say, a lot of people ask me, what's a good model? What's a good way to do sensitivity analysis? What's the good way to do uncertainty analysis? What's a good way to do model validation? And I start with, it all depends on what the question is you're trying to answer. And those could be quite different for different kinds of questions. So I could have just blown by you with all the sea level rise and climate system stuff, which is really complicated, and totally left out the ocean acidification. And there may be other ones like this methane trapped in the tundra or the cloth rates and so on. So
I already see with sonar, you can already see the methane boiling out of the offshore, again, in Nordic waters. You can see it boiling out.
Yeah, so we got to get these observation systems. That's the other element that was pretty well represented in International Academy thing, is we got to get the Earth observing system, A, to actually have the resources to make the measurements, and B, to feed it back on a timely basis. My department chair, Elizabeth Cornell, did the O-ring problem, and it was quite clear that 2 or 3 levels of engineers knew this was a huge problem, and it never got up till the actual launch control decision.
Actually, it was decided to go because of bureaucracy.
Yeah, actually, Elizabeth did in the same conference. I had not known that.
Management made a decision while engineers were saying, no, it was freezing out there last night.
That's the bit went up, bottom up.
Right.
Change from no to yes.
Yeah, so in climate change, we want to avoid that.
Well, let me just bring something up, and this is totally separate in a sense, but it's the same thing. So are you aware of the report that JFK asked for, got in 1962, about America's energy future?
Boy, 62. I'm very good friends with George Shultz, and he can tell this story, but starting about 15 years after that. President after president said, energy security is a big problem, George, go figure that out. 5 years later, not a problem, forget about it. 5 years later, big problem. I don't go back to... So in
1962, JFK asked a few Nobel winners to determine America's future for nuclear power. And they wrote a report that was delivered actually 49 years ago today to JFK, which explained how by 2000 we would have no more burning of coal or oil. in the United States.
Well, there was a famous 50s book run through one of the Washington think tanks that had the statement, you probably heard this, nuclear power would be too cheap to meter.
Well, that was simply marketing. But the point is that these folks actually were quite concerned with climate change and wasting petrol products, because that's what we do.
Yeah.
We burn things we can make stuff out of.
Yeah.
So not only was global warming known before 1970 as a serious problem by scientists, it was also known how to fix it. And we didn't do it.
Yeah.
So now what's to say that anything that we're doing now is actually going to really fix it? Because now we've built in 50 years of emissions that are in the ocean mostly now.
Yeah, so we're at a riskier point in time than we
right.
would have been if we were active.
We would have
sooner.
half the problem we have now.
Yeah. Well, I definitely ascribe to that view, and it is concerning that there isn't more immediate attention being paid to this. And of course, people are saying, "Well, doesn't all your funding?" And actually, all my funding doesn't come from this kind of stuff, but some of it does. So it's just it's a battle. So you got to, pick your places and take your best shot. So I just got my guys this morning after this conference and said, you'll be happy to hear that we got to do more on uncertainty. Let's not forget. And I just heard that the US GCRP released their draft report amid great protestation with not a word about uncertainty. US Global Change Research Program. So they're now going to try to get a supplement put on that. So at least the US scientific community should know better than that. And hopefully we can get that kind of stuff in the international reports as well. So I think that this framing issue is really something that does get left by the wayside, and it's a good, back to my previous parable about why you do modeling, it's a good way to make really big mistakes without realizing it. Like burning down all the rainforest to get the biofuels. And these are people who have been in this field. That Jay Edmonds, who's the chief scientist in that group, is actually mistaken for an ecologist or a climate modeler, though he's an economist because he knows so much about it. And until he actually made the model runs, unfortunately, he knew something was wrong right away. But the first couple of weeks that this stuff came through, he said, "Oh, amazing! It's so easy to do this knockout. It's a knockout. It's a silver bullet."
I'm interested in your assessment as an outside person. It looks to me like the vast preponderance of the risk is on a bad outcome. That there aren't too many good uncertainties toward a good outcome here. That we are really very much at risk in terms of a couple of bad things come together. It could be really bad.
Yeah. Well, Carl, that's my comment that I made with Keeling. Keeling recognized this in the late 70s when he was studying CO2. And he paused to make people think.
So what do you think in terms of the assessment of the risk, in terms of a bad outcome as opposed to a more pleasant outcome in this business?
Well,
are the risks piled up for a bad outcome?
Yeah, I think it's just a matter of degree as to how bad, but I think it's certainly worse than the expected value picture paints. But that's a problem because most of the detailed research, again, with all the bells and whistles, has been done around rain, not around the extreme. There's a kind of wobbly, a good friend, economist Marty Weissman, a Harvard guy, who's been pushing for the thick tail formulation of the problem, and I think that's useful. I don't actually agree with the specific way that he's formulated it, but it actually just makes you think more about the extremes than the means. It's hard, the other frustration I have with the scientific community on this is that you'll go, well, what are your extremes? And they're very hesitant to say, this is what we're really worried about. And I go, well, if you're not going to do that, if you're not the one that's going to brainstorm about that, you're going to have stakeholders, political hacks, I don't want to pick on Rush Limbaugh, somebody like that, will actually fill in the blanks. Or me, even me, I could do that, but I don't really want to play Richard Alley's role or the people that study ocean circulation or this. One thing I do fear is that there aren't that many experts in some of these ocean acidification. It sounds like there are.
Well, there was an article in Science not long ago about that.
Yeah.
And you can see they had samples.
Yeah.
For more, please visit us at stanford.edu.